And welcome back. In this chapter we will explore the topic of dynamic programming. That's a method of breaking down a problem into simpler subproblems, and it can be used in countless situations. I would say that this is the most important technique out of all the algorithms we've discussed, as it is so universally applicable. But let's start with a simple example. Now have a look at the container of length n. You've got two building blocks, one of length 1 and one of length 2, to fill the container. Like that, or like that. Okay, your task is to find out on how many ways you can fill the container. For n equals 4, these would be the possible states. So the result would be 5. Now, how would you solve this problem? Not that easy, right? Let's have a look at the very last block. There we only have two options. Either the last block is a small block or a big block. So we can say that the number of possibilities of length n is equal to the number of possibilities of length n minus 1 and then add a small block, plus the number of possibilities of n minus 2 and then add a big block. This way we do not count any cases twice, as the last block is always different. So we found a recursive formula. P of n equals P of n minus 1 plus P of n minus 2. This formula looks kind of familiar. Anyways, the only thing left to do is to define our base cases. For a container of length 1, there's only one possibility, and for a container of length 2, there are two. So let's write our program. Perfect. Now let's test it. P of 4 is 5? Nice. And P of 45 is... Wait, it's taking forever! And it's only number 45! What's going on? Let's have a look at what we are calculating. For P of 7 we need P of 6 and P of 5. For P of 6 we need P of 5 and P of 4. And for P of 5 we need P of 4 and P of 3, and so on and so on. The tree grows rapidly, and we have an exponential runtime. But we can see that we do a lot of redundant work. For example, we calculate P of 5 here and there, and we calculate P of 4 there, there and there. So what about memorizing the results of P instead of recalculating them every time? We modify our code to save the results in an array or map. Now, before we calculate anything, we check if the value was already calculated, and if yes, we return the value and do not recalculate it. Our search tree now looks something like that. The gray values indicate that the saved value was returned. By using this technique called memoization, we not save something like half of our runtime, but we reduce the runtime from exponential to linear. Incredible! Now, memorization works fine and seems intuitive, but most of the time we can use a much simpler approach to solve these tasks. Once we realize that we need to calculate all the previous values of P anyways, we can use a bottom-up strategy to come to our result. So we first initialize our base cases n equals to 1 and n equals to 2. Then we start with I equals to 3 and calculate the value from the previous ones. Our result now is the nth value in the array. This way, our complicated recursive function with memorization simplifies to a very easy for loop. And this approach can be used every time a problem can be broken into smaller subproblems, as long as these subproblems only refer to previous states. Today we learned how dynamic programming can be used to solve problems by breaking them down into smaller subproblems. By using a bottom-up approach, most recursive functions can be resolved. Because this topic is so important and far-reaching, we will have a look at two other examples where dynamic programming can be used in the next videos. So, I better see you there!